G'day team, welcome back to yet again another video on calculus. Now last time we actually looked at where everything was leading to and we sort of looked at the derivative function. Now we did it in a pretty long way and we'll go through another example just as a bit of sort of revision. But from last time we introduced a bit of notation as well. So my derivative function dy by dx or f dash of x is the gradient of a curve at x. Now, dy by dx equals f prime of x, we said was equal to this formula here. So the limit as h tends to 0 of f of x plus h minus f of x all over h. Now, this was differentiating by first principles. And it is really good to know. It's one of those things that it's nice to know where the little tricks you'll learn come from. So let's just do another quick example using differentiation by first principles. So I've got f of x equals x squared. That means f of x plus h is x plus h squared. So let's substitute those in here. So the limit as h tends to 0, now I've got x plus h squared minus x squared all over h. Now I need to expand out that top line. So the limit as h tends to 0, x squared plus 2xh plus h squared minus x squared all over h. Now we can see that those x squareds cancel out, leaving just two terms, both with a h in it. So what I'm going to do, I'm going to take out that factor of h in this step here. So h at the front, 2x plus h all over h. Now, those h's can cancel out, and I'm left with the limit as x tends to 0. Oh, x. Silly me. That is a h in there. So as h tends to 0 of 2x plus h, we can now apply my limit. So f dash of x is equal just to 2x because this h becomes 0. So it's a really long process to show that for f of x equals x squared, the derivative function is just 2x. It's a really long process. So we're going to go through a little way to shortcut this process a bit. Now, I've got a whole bunch of different polynomial terms here. So I've got f of x, my function. So x squared, x cubed, x to the power 4, x to the power 5, x to the power 6. Then I've got my derivative function of each. Now we just showed that for x squared, the derivative function is 2x. In the previous video, my example was x cubed, and we showed that that was 3x squared. Now I've gone ahead and done the other three. Pause the video now and try and see if you can find a pattern between these this table here. So have a quick moment, have a think about it. All right, so hopefully you identified that the power comes out the front and multiplies the x, and then the power itself drops down by 1. So in x to the power 5, the 5 comes out the front, and then the power of 5 drops down by 1 to be 4. So if we see a term of x to a power, so we're going to call this the power rule of differentiation. We bring the power out the front and we drop the power down by 1. So really handy rule because it's going to save us a lot of time. So let's have a look at the following. Now, my function f of x equals 7x cubed plus 4. So that means f dash of x equals, now the 3 comes out the front and multiplies, and then my power of x drops by 1. Now, if I have just a constant term, there's no x there to differentiate, so that becomes 0. So if I simplify this, I've got 21x squared. Now you may notice that the 3 comes out and multiplies by the 7. So if you're comfortable skipping this little step of writing here, more than free, and I'm going to start doing that now. So in part B, f of x equals 3x squared plus 4x. So f dash of x equals. The 2 comes out the front and multiplies by the 3 to give me 6. The power 2 drops by 1, so I'm just left with x to the power of 1. Now, I've got to do this term as well. X is currently to the power of 1, so 1 comes out the front and multiplies to be 4. And then my power drops to 0. But anything to the power of 0 is just 1. So that means I've got 4 times 1, which is just 4. So if you see something multiplied by an x just by itself in my function, the derivative is just the coefficient at the front. If x is by itself, then we just replace it with a 1. All right, this is where it can start getting a little bit tricky. Now there's a square root in there. We cannot apply the power rule of differentiating to a square root. So what we need to do is we need to convert that to index form or to power form. Now you should hopefully remember from previous videos, let's just rewrite my function here. So f of x, not f dash of x, f of x, so 12x cubed minus 7. Hopefully you remember that square root of x is x to the power of 1/2. Now that we've got it in index form, we can apply the power rule. So that means f dash of x, now that we're doing our derivative, 3 comes out the front, multiplies by the 12 to get 36, and then the power drops by 1 to 2. Then in the second term, 1/2 comes out the front and multiplies. So I've got negative 7 on 2, x, and then I have to still take 1 away from 1/2. So 1/2 minus 1 is minus 1/2. Now, it's starting to get a little bit complicated, but we don't want to have negative powers in there. So going back to our index laws, we want to take that term to the denominator and make the power positive. So I've got 2x to the power of 1/2, but x to the power of 1/2 we know is just the square root of x. So we're going to resubstitute in all over 2 square root x. Now, because the question has given it in the form of a surd, I want the answer in a surd, okay? So we have to do this process of bringing it down to get the full marks. All right, we've got 2 more examples, and then you guys will be off and hopefully ready to go. All right, I've got f of x equals x squared on x squared minus 2 all over x, sorry. Now, the biggest mistake I see people do is go 2x minus 0 over 1. Okay, we can't do the derivative of each individual term. So what we need to do is we need to split this fraction up. So f of x equals x squared on x minus 2 on x. Now, we can simplify this a little bit further. So I'll bring it up to the top now. So f of x equals just x squared divided by x is just x, minus 2 on x. Now I said just before, we can't have a square root, or we can't apply the power rule. We also can't apply the power rule if my x is in the denominator. So I have to bring that up to the top. So my function is now x minus 2 times by x to the negative 1. And now we can apply my power rule. So f dash of x equals, remember x by itself goes to 1. The negative 1 comes out the front, so negative 1 times negative 2 is positive 2, x, and then minus 1, take another 1 is negative 2. Now, just like surds, we don't want negative powers in there, so we're going to take that back to the bottom. So I've got 1 plus 2 on x squared. Okay, so from something that looks fairly simple, it does get a little bit complicated. Okay, so there's a few rules that we need to adhere to. No square roots in my function. Got to put them in terms of powers. And then I also don't want any x's in my denominator. So we've got to use negative powers to get them to the top. So let's do one more example. So f of x equals 2 over root x. So let's manipulate our function a little bit to get it in the form we like. So turning the square root into a power, and then bringing that x term to the top by changing the sign of the power to be negative. I can now apply my power rule. So f dash of x equals negative 1/2 times by 2 is just -1. Okay, and then x, negative 1/2 minus 1 is -3/2. Okay, so we're getting some crazy fractions here now. Now let's take that x back to the bottom. So I've got -1 all over x to the power of +3/2. Now, inside here, we have one whole 2/2 and another 1/2. So what that means is we can write this as x to the power of 1 times by x to the power of 1/2. Because when we bring these together, we add those and we get 3/2. Now, x to the power of 1, we can just write as x, and x to the power of 1/2, we can write as the square root of x. And that is my most simplified form. So f dash of x equals -1 on x root x. Now, there's a lot of things to still keep in mind, okay? A lot of practice on these is going to do a lot of good when we start getting into the really meaty stuff, all right? Hopefully this has helped. Hopefully you're glad you don't have to do differentiating by first principles for much longer, and we'll see you in the next video.